Assalamu alaikum. In the last lecture, we were talking about white box testing techniques. We talked about what white box testing is, and we discussed basis path testing, condition testing, and loop testing in quite a bit of detail. Today, we are going to talk about black box testing, and we will talk about the issues and techniques in black box testing. So let's start our discussion related to black box testing. Black box testing focuses on functional requirements of the software product, and it enables the software engineer, like a person like me or you, to derive sets of input conditions that will fully exercise all functional requirements for a program or for a software product. It is not an alternative to white box testing. Rather, it is a complementary approach that is likely to uncover a different class of errors. I'm sure you remember what white box testing does. White box testing primarily uses software code to find errors in small units like individual units and modules, and it exercises test cases that ensure that all statements have been executed at least once. It looks at the data flow, it looks at the control flow, and it also looks at conditions and loops for testing. But here, that is in the black box testing, the focus shifts from in the small to in the large. And the black box testing uses functional requirements of the software as a mechanism to test. Black box testing is focused on finding defects at finding requirements defects, finding defects which relate to the product as a whole, which the customer would immediately find out if they are available in the, or if they are found in the product. Here you have a picture that shows black box testing. This picture, you can see that there are inputs coming into the box, and then there are outputs produced by the box. And there are certain events and requirements that are actually controlling this box, but you cannot look inside the box. So what this means is that when you are performing black box testing, you cannot view source code. You cannot read source code. In fact, you do not have access to source code. You cannot look at the data flow. You cannot look at the control flow. You can only look at the interfaces, the external interfaces of the software program, or at a larger level of a product. So you can only send inputs to the product, and you can only expect outputs or results from the software product. And so your interaction, your interface with the software product is through the inputs and outputs only. And this form of testing is black box testing. And so if I restate what black box testing is, I can say that black box testing is a testing approach, software testing approach, in which we try to find errors of the following categories. Number one, incorrect or missing functions. Number two, interface errors. Number three, errors in data structures or external database access. Number four, behavior or performance errors. And number five, initialization and termination errors. This last category of errors deal with those errors where we try to initialize certain programs, or when we are terminating programs or terminating the execution of software product and errors encountered at that time. And so you would notice that these kinds of errors belong to the product as a whole and not to individual units, individual modules, individual components within the software product. And so we can say that the scope of black box testing is higher or broader as compared to white box testing. We can also be sure that black box testing usually follows white box testing. That is, white box testing is performed before black box testing, as we had discussed in an earlier lecture. Another very important thing that you must keep in mind is that the black box testing purposely disregards control structure. Attention is focused on the information domain. While when we were talking about white box testing techniques, we emphasized the fact that the entire focus on white box testing is based on control structure and the availability and the visibility of control structure to testers and test designers. Here it is the opposite. The black box testing is based not on control structure, and it actually disregards control structures. It is not privy, the testers and test designers are not privy of control structures and control flow within programs in the software product. And the attention of test designers and test performers or testers is focused on the information domain, the domain which contains the software application. And tests are designed to answer following important questions. We will take each question and have a little bit of discussion on that. The first is, how is functional validity tested? We have to look at the functional requirements. We need to determine from the expected inputs and the expected outputs on what are valid results. And so, as I said, that the focus shifts to information domain. The information domain is going to provide, is to help us in answering this question as to how the functional validity be tested. The second question is, how is system behavior and performance tested? And obviously this is directly related to the requirements, and the requirements would have answer to that what are the acceptable performance ranges in certain situations, and what is the expected behavior of the software product in both normal circumstances and exceptional circumstances. And these informations are also dependent on the information domain. And the test case designers would have to take those requirements and then develop test cases so that the requirements are captured in those test cases. And at this point brings my attention, and I would like to share it with you. One of the things that we had talked about earlier in when we were introducing software testing, is that all tests and test cases should be traceable to requirements. And the third question is, what classes of input will make good test cases? That naturally depends on the requirement set and how the software has been developed, because the interface is available for us to look at, and the interface will enable us to develop a class of inputs that we can use as test cases. So black box testing is going to focus on these questions. Well, the fourth is the system particularly sensitive to certain input values? And this information is obviously going to come from the requirement set as well as the application domain. Next question is, how are the boundaries of the data class isolated? What are the possible acceptable values as far as inputs are concerned, and what are the boundaries that are acceptable? And how we isolate them is as a question that the black box testing experts have to answer. And what data rates and data volume can the system tolerate? And this deals with the reliability and performance aspects of the software. Another question is, what effect will specific combinations of data have on the system operation? And this also deals with the characteristics of the software. So you see that all of these questions primarily lead us to the requirements set. And so all of this information will be gleaned from the requirements model. And the interfaces that have been developed, that have been published by the software engineering group, will help us in narrowing down the boundaries and narrowing down the classes of inputs and also the classes of outputs. But again, the outputs, since are dependent on the inputs, will also be are dependent on them, and also should be traced to the requirements, because the requirements actually state the expected results also. And so black box testing is based on the requirements model, and the more accurate and complete set the requirements model will be, the planning and preparation of test cases for black box testing will be more accurate. If there are problems in requirements, certainly those problems will be reflected in black box testing. And so you see, now we have a chain of activities that start with the requirements and continue with design and development and testing and further on. And so all of these major activities in software development lifecycle are related to requirements directly. By applying black box testing, we derive a set of test cases that satisfy two very important criteria. Number one, test cases that reduce the number of additional test cases that must be designed to achieve reasonable testing. That is, we want to have a minimal set of test cases that can achieve the targets, achieve the goals of black box testing as completely as possible. We do not want to test, have a large set of test cases. Number two, test cases that tell us something about the presence or absence of classes of errors, rather than an error associated with only a specific test at hand. So we would want to develop test cases such that they uncover a class of errors. That would be a very good test case design. So as black box test case designers, you need to be experts in achieving these two criteria that we have discussed. So software testing, especially black box testing, is a very useful and a very important activity in software development life cycle and software development process. In fact, if you look at it comparison-wise between black box and white box testing, so black box testing is more interesting and more challenging as compared to white box testing. Because when you have the source code available to you, you can look at the code and you have a better chance of finding defects. But when you're performing black box testing, that code is not available to you. And you have to be very smart in order so that you can generate test cases which will be successful. Remember, a successful and a good test case is one which finds defects. So black box testing is a challenging software development activity. Let us now focus our attention on black box testing techniques. Primarily, we will talk about equivalence partitioning and boundary value analysis. Let us discuss equivalence partitioning first. Equivalence partitioning is a black box testing method that divides the input domain of a program into classes of data from which test cases can be derived. So the first thing is that you have to look at the input classes. We have access to the interfaces of the programs that are going to be tested. We look at the interface, we have the test planning document with us, and we divide the expected input into different classes. And I'll give you an example in a little while. Equivalence partitioning strives to define a test case that uncovers classes of errors, thereby reducing the total number of test cases that may be developed. And this is a concept that I stated a little bit earlier also. The example that I was going to give you is, let's say that a program expects an integer. And you are looking at the possible input classes. If you think for a minute or so, and I ask you what are different classes of input that can be made out of integers, you would immediately think of 3 input classes. There may be more if you go for very detailed analyses, but broadly speaking, you can have 3 classes of input when you're dealing with integers. You can have positive integers, you can have 0, and negative integers. You can have numbers from 1 onward to infinity, you can have 0, and you can have -1 down to any smallest number. And so when we are talking about equivalence partitioning, we need to break the input data into possible classes, just like I did for an integer set. This is important because for an integer, some of these, or we have 3 classes here, all of these 3 classes may be valid input. But in certain programs or in certain software products, only positive numbers or positive integers would be acceptable, or possible inputs. In certain scenarios, only negative integers or negative numbers are acceptable, while in some other products, a combination of 2 would be acceptable. And so when we are using equivalence partitioning, the first step is that we need to separate the input data into partitioned classes so that we can isolate valid and invalid input data. An equivalence class represents a set of valid or invalid states for input conditions. And so the first step, as I said, is going to be to separate the possible input values into valid sets and invalid sets. This is an example that I've given to you for an integer. Typically, an input condition may be a specific numeric value, a range of values, a set of related values, a Boolean condition. And I'm leaving out the possibility of character sets and other complex data structures. I'm taking simple things at this point. And so for even simple things, you see that multiple classes and multiple options are available even for input. I've taken an example of an integer. If I make it a little bit more interesting, I say a real number is expected as an input. Now the possibility of the real number opens up a substantially large input class, because you know that real numbers have two aspects to it. And if we are dealing with fractions, then the precision would bring in all the complexity. How precise the floating point number should be. And so the possibility of possible input values increase substantially, many orders of magnitude. And so this equivalence partitioning approach helps us in determining and in categorizing different classes of input data. Very important concept. Now let's talk about the guidelines for equivalence classes. If an input condition specifies a range, one valid and two invalid equivalence classes are defined, because you have a range of, let's say, numbers. And so you would need certain input data that lies inside that range, that is valid number, valid input. And one input set you would require for the range, or for the lower side of the range, and one for the higher side of the range or upper side of the range. If an input condition requires a specific value, one valid and two invalid equivalence classes are defined, again on the higher end and on the lower end. If an input condition specifies a member of a set, one valid and one invalid equivalence class are defined. And this is because sets are not necessarily ordered. They would become range if they are ordered. At least in this situation, we are talking about unordered sets. And if an input condition is Boolean, one valid and one invalid class are defined. And so these are the minimum classes that you would require for testing using the equivalence partitioning approach. Here you are looking at a picture which shows equivalence partitioning. You have one set partitioned as user queries, one set partitioned as mouse picks or mouse clicks, another set as output format, another set as prompts. Then you have function key inputs and data as another partition shown here. What this picture shows you is that all different classes of inputs and outputs have been separately partitioned. And for us to find appropriate test cases, it is very important to classify these inputs and as a result classify outputs also, so that we can fully understand the accuracy of the software program. Let's now talk about a little bit on these equivalence classes. Typically, you can have valid data and invalid data. Valid data includes user-supplied commands, responses to system prompts. You can have one class as file names. You can have computational data, which consists of physical parameters, which also can consist of bounding values or initiation values. You can also have output data formatting. You can have responses to error message as another class, and you can also have graphical data, mouse pics, for example. And then you must also separate out the invalid data. And invalid data would mean data outside the bounds of the program, physically impossible data, or proper values supplied in wrong places. These are examples of invalid data. So when we are using partitioning, equivalence partitioning approach, the first step is to develop classes of input data elements and also to develop classes for possible outputs from the program. Then and only then we can determine if the valid data or accurate data produced accurate results. And with the help of classes of data, we can determine the accuracy of the program. So the example, let me go back to the example that I was discussing in the beginning here, is that let's say that we have an integer as an input, and we separate that into 3 classes, and all of them are valid, and we determine that if we give negative integer as an input, whatever the number may be, we get an invalid response from the system. But if we give 0 or positive integer, the results are accurate. But the system allows all integers as possible input values. So in that case, we can isolate the problem by noting down that negative numbers have not been properly handled in the software or have not been taken into account while developing the algorithm. And so an entire class of input values have as a result been not handled. And although this is a very simple example, this shows the importance of not only developing classes of valid and invalid data, but it also helps us in determining the accuracy of the software program for an entire set of input values. For example, the number can be -1 or number can be minus 5,223. And so if the results are predictable, then we can say that the program contains errors with respect to this range of numbers or with this class of input values. And this sort of information can be very useful for people who are actually going to find the defect and repair them once this test has been, this observation of failure has been reported to them. And so we see that equivalence partitioning is a very important part of black box testing. There's another thing that I would like to mention here, is that I have explained to you this equivalence partitioning in a very simple terminology. But as the improvements and research and progress in computer science, software engineering, and statistics have led us to benefit from research in different areas, software engineering and software testing has benefited certainly from work done in statistics. And a lot of work has been reported in literature that uses statistical models to determine these equivalence classes and partitioning. Just as I was saying that an integer can be broadly broken down into 3 classes, we can state that this fact with the help of statistical terminology. And different authors and researchers engaged in software research and software testing have chosen to do this. But to convey this concept in simple language is easier, and therefore I have chosen to follow simpler terminology and not confuse a lot of you in statistical details. And so you will find literature which uses statistical terminology and in determining and dividing or describing this concept of equivalence partitioning. Just remember the concepts that we have discussed here. Again, summarizing what the benefits of equivalence partitioning are, is that it helps us in identifying valid input data, valid output data, invalid input data, and invalid output data. And that way we can determine if the functionality of software is really present or not, based on the inputs, the algorithms produce the results, if they are acceptable or not. And so equivalence partitioning is a very important and fundamental black box testing technique. Let us now discuss the boundary value analysis technique. This is a testing technique which comes also under black box testing, and which leads to the selection of test cases that exercise bounding values. This is because that for reasons not clearly and completely understood, a greater number of errors are found at the boundaries of the input domain rather than in the center of the input domain. So what we would want to do is to determine what are the boundaries of the input domain, and try to test those boundaries or bounding values with special care, so that we don't make mistakes there. The boundary value analysis approach complements the equivalence partitioning testing technique, and both of them help us in conducting very effective black box testing for software products. Here you can see the boundary value analysis again in the pictorial form. You can see that for all those categories of data where inputs or outputs have any sort of bounding values, we need to determine what are their boundaries. So what are the boundaries for mouse picks, what can be the boundaries for output formats, what can be the boundaries for prompts, for function key inputs, for data, and what are the boundaries for output domains. These bounding values or boundaries will help us in testing the bounding in much more detail and in an organized manner. So the combination of equivalence partitioning and boundary value analysis helps us in developing highly effective test cases for black box testing. We want those test cases which are able to find as many defects in the requirements of, as well as many defects at the requirements level when we are conducting tests. We want to have these test cases determine a large or an entire set of classes of errors that are left by mistake into the software product, and we would want to design test cases that can determine the errors at the errors of functionality, errors at the initiation and termination of the software product. And so black box testing is an important and high order testing technique and set of techniques without which we cannot deliver the product to the customer. There are other black box techniques also. I would like to mention state testing technique. This technique uses equivalence partitioning techniques to determine test cases. In this technique, we determine the state of the software product. Previously, we were focused on the different classes of inputs and the results that will be produced as we provide those inputs to the software product. But when we are doing state testing, we look at the different possible states that a product can be in at any given time, and then we look at the state transitions that happen as a result of the execution of the software product. And so state testing is also a very important aspect of black box testing. It helps us in determining that all the software product has entered and exited from all possible states that it can be during the execution, and the issues that relate to state transitions are also handled at state while we are performing state testing. And so black box testing is a very important part of the overall testing strategy that is developed for any software testing activity. Clearly, it is different from white box testing. If we summarize the differences, once again, to convey and to show the benefits of both, the white box testing is done in the you can also call it as testing in the small, while black box testing is testing in the large. Timeline-wise, black box testing comes later after white box testing has been performed. The perspective clearly is in white box testing is to look at the code and develop tests based on the code to determine the control flow and data flow. The focus is on basis path testing, condition testing, and on loop testing, while in black box we have no idea of the control structure of the program. We only have access to the requirement set. We have access to the interfaces of the program, and we know what type of input is expected and what type of output will be produced. We do not know the exact values, but we do know, but in certain situations, in simpler cases, we may know the exact output value also, but mostly we know the ranges or possible values as a result of the execution of the software test or software product. And so if you look at from the tester's perspective, white box testing is conducted by the programmers themselves. On the other hand, the black box testing is conducted by a special independent group of testers who are part of the project team, and in certain critical projects this may be done by third-party testers, and we call that group as IVNV group, or independent verification and validation group. This typically is this group is typically used where the project is of very high critical value in terms of the money, in terms of the importance to the national projects, and especially for defense-related projects and for large aero or large avionics projects, IVNV groups are used for black box testing. And so black box testing is a very important part for checking the functionality, for testing the functionality of the software product. And for small projects, typically the testing activity ends when black box testing is finished. However, for large projects and for certain special projects, there are other testing activities that are conducted after this black box testing. In the next lecture, we will talk about testing strategies, and we will see in detail what kind of testing approach should be used. These were the testing techniques that we have discussed. We will look at testing strategies in the next lecture and continue our discussion on software testing. So see you then.